Okay, so I'm going over quiz number 3 right now. Um, got a couple of requests for that. So looking here, what is the coloring for K7? So that's just going to be 7 because K7 is complete graph on n vertices, and complete graph on n vertices is always has that m as its coloring, because every single node is adjacent to every other node, so it can't be the same color as that node. Here we've got another similar rule. If we have an odd cycle, it will always be of its coloring will always be 3. If we have an even cycle, its coloring will always be 2. You can prove that to yourself, basically inductively, of start off with your smallest odd cycle of a triangle, and then just keep on adding pairs of vertices. But that was also something we covered in the notes. How many colors are required to color a tree with 6 vertices such that the root connects to one node, and all of that stuff is irrelevant. A tree requires 2. That's it. There are no cycles. It requires 2. So is this graph planar? The answer is yes, because it can be written without the edges crossing. Voila. So this is an Eulerian circuit. You can tell by the fact that all of the degrees are even. If it was an Eulerian path, 2 of them would be odd and the rest would be even. And it might be Hamiltonian, but I don't know. I would have to go through and check. But I don't see any reason just by this description that would definitely have to be Hamiltonian, versus it definitely has to be Eulerian. This also similar rule, it has exactly 2 odd, so it's going to be Eulerian. Has an Eulerian path. Which of the following has a Hamiltonian path? So this is going to be pretty easy to check for some of these guys. A tree, a 5-star tree, is obviously not going to do it if you just draw what it looks like. Annotate. So it's going to look like 5. So if you start off in the middle, then you can only go out to 1. If you start off on one of the edges, you can go into the middle and then out to 1, but then you're not going to touch any of the other 3 outsiders. Cycle is easy. I think that's actually 6, but it doesn't matter. Put an extra one there. Right there. You just go around the circle. K9, again, it's super connected, so you can just draw it so that it's in a circle and go around the circle. Just connect to whatever has not yet been connected to. And then the underlying bridge for 7 Bridges of Königsberg, you guys can go through and actually draw that out and see that it is the case. If I pick this and this, then they only connect to this, which gives me the subset of the top, such that the cardinality at the top is strictly greater than the cardinality at the bottom. Therefore, I know that it is not, that there does not exist a perfect matching. And so I pick my first vertex. It's connected to 4 other vertices. So that gives me 4 edges, then 3, then 2, then 1, because I can't double count these. Or I don't want to double count these. I could also use the fact that we have the formula n times n minus 1 over 2, or n choose 2. for the how many edges are there. So I give you guys a few different proofs for that in the notes. Degrees. So this is the same basic idea, except we end up doubling it. So we calculate the fact that there are 21 edges, but the degree is twice the number of edges because it produces one on each side of the edge. C9, this is what is the sum of the degrees. A cycle of 9 has 9 edges, and then you just multiply by 2. How many edges are there on a tree with 11 vertices? The formula for the number of edges on a tree on n vertices is n minus 1, and we prove that inductively in the notes. Cool.